Okay, some solved problems for chapter 37. As always, do give these a shot yourself before watching my solutions. So here we are, and we're going to be in our space utility vehicle. And so this is going to be us, and then we're going to get passed by a rocket ship. And she actually has a speed of 0.8 multiplied by c. And draw her kind of whizzing right along right over here. Now, a couple things to kind of keep in mind is we're going to measure time, and she's going to be measuring proper time. And we can actually solve this guy any number of ways. The first thing you should always do when you're doing one of these guys is just go ahead and calculate that gamma value, because we're always going to need it. And it's going to work itself out to be 1.6 repeating. We could use time dilation, we could use length contraction, and we can also use distance equal to rate times time. We could do it either way. I'm actually going to answer part C first, and I'm going to say that the time elapsed is going to be equal to the distance that I measure divided by the speed of the spacecraft, and so that's going to be 1.2 times 10 to the 8th meters divided by 0.8 multiplied by 3 times 10 to the 8th, and the time that I measure is going to be 0.5 seconds. Now I can answer part A, what is the time elapsed by the spacecraft? Again, this is proper time. That's going to be the time that I've measured, which is 0.5 seconds, divided by gamma, which is 1.6, and we're going to get 0.3 seconds. And we get a warm fuzzy feeling about this because the smaller amount of time has elapsed for her than it has for us. And lastly, for part B, we could do length contraction using this value right over there. Or we could say, hey, you know what, we can use just distance is equal to rate times time, so length is going to be equal to the speed multiplied now by the time elapsed, and this is going to be by the spacecraft. And if we can say, okay, well, we know that this is 0.8 multiplied by 3 times 10 to the 8th meters per second, multiplied by the time, which is 0.3, and we're going to get 7.2 times 10 to the 7th meters, and we get a warm fuzzy feeling by this because this is smaller than the value that we measured. So for problem number 9, we're going to be looking at length contraction, and here we have something that is moving at 0.6 c, and someone on board this thing measured the spacecraft moving to be 74 meters, and then it lands, and we're going to measure the stationary spacecraft. Now, how big is it going to be? Well, we know that this is going to be U, and this is actually going to be L, and we're looking for L naught here. And so what we can kind of say is we know that we can write L naught, that's going to be equal to L divided by 1 minus U squared over C squared, and that's going to be 74 divided by 1 minus 0.6 squared, and it's going to work itself out to be 92.5 meters. And if you ever kind of get confused about, which one is L, which one is L naught, if you do your calculation and it, in this case, if L were to get smaller, then you know you did something wrong. You know that this thing should be longer when it's on Earth, or when it's on the land or not moving compared to when it's in motion. So let's get a little bit of practice using Lorentz transformations, and here we're going to have our reference frame, and we're going to have some moving reference frame. And the only tricky thing with this is, do I give you, v prime and have you figure out v, or do I give you v and have you figure out v prime? We do know that this guy is moving at a speed with u is equal to 0.6 c. And I'll do part A and I'll let you work out B and C. We're interested in this guy right over there, and we're given v prime, and so it's going to be equal to 0.4 c plus 0.6 c. You can kind of see that's going to add up to 1 c, and we know that is physically impossible, so we need to divide by a larger number. So that's going to be 0.4 c times 0.6 c. That's going to cancel out with that c squared, and we're going to get 0.806 multiplied by c. And I'll let you type them in. You can kind of see as we go faster and faster and faster and faster, 0.974 c, and then 0.997 c as we're going faster and faster and faster and faster. Okay, so let's get some practice using relativistic forces. If we have some force acting on an electron due to anything really, an electric field, let's figure out the acceleration if the speed is non-relativistic. Pretty straightforward. Acceleration is going to be equal to force divided by mass. So that's going to be 5 times 10 to the minus 15th divided by the mass of an electron, which is going to be 9.1 times 10 to the minus 31. And we're going to figure out this is 5.49 times 10 to the 15th meters per second squared. Now let's do it in the relativistic sense, and right over there that tells me that my speed is going to be 0.83 repeating multiplied by c. And essentially what I'm going to do is I'm going to say that the acceleration is going to be equal to the force divided by the mass, only this is the relativistic mass. It tells me that the force is parallel, so that tells me that this has got to be gamma cubed. If it was perpendicular, then it would just be gamma. So what is gamma? Well, gamma is going to be equal to 1 divided by the square root of 1 minus 0.83 repeating squared. And so that's going to work itself out to be 1.81. And so this is simply going to be equal to 5 times 10 to the minus 15th divided by 1.81 cubed multiplied by the mass, 9.11 times 10 to the minus 31. And we're going to get now an acceleration of 9.26 times 10 to the 14th meters per second squared. And what's kind of going on behind that is now we have to overcome essentially a lot more mass, and so the acceleration is going to be much smaller when it's moving very fast. And a little bit of practice using relativistic momentum and energy. We have a muon, which is a subatomic particle moving at 0.999 c. Let's calculate the momentum and energy, and the mass is going to be 207 times more massive than the mass of an electron, which we know what that is, 9.11 times 10 to the minus 31. So let's go ahead and I'll spare you the gory details of that. This is times 10 to the minus 28th kilograms. And of course we always need what gamma is, and that's going to be 1 minus 0.999 squared. So gamma is going to be equal to 22. And we're just going to say that relativistic momentum is going to be gamma times the mass and the speed. And so that's going to be equal to 22 times 1.89 times 10 to the minus 28, and then 0.999 times 3 times 10 to the 8th. And we're going to get a momentum that is 1.27 times 10 to the minus 18th, with of course units still of kilogram meter per second. The kinetic energy is going to be equal to gamma minus 1 multiplied by mc squared, and so this is going to be 22 minus 1 multiplied by 1.89 times 10 to the minus 28th multiplied by 3 times 10 to the 8th, which is going to work itself out to be 3.63 times 10 to the negative 10th joules. And we could also do a really quick joule to electron volt conversion, where 1 electron volt is 1.6 times 10 to the negative 19th. And so we could also get this is going to be 2.27 times 10 to the 9th electron volts.